All right, so in this video, we're going to get started with higher order functions. And so we're going to go through a few things today. So the goal of higher order functions is being able to treat a function that you've built and used in Python as a source of data. So this could be arguments to another function. This could be a function that returns a new function. And so what we're going to start with is just using a function as an argument to another function. And the question is, why are we doing this? Well, when we're working with functions, there's a few different things. In general, this is a way for us to write programs that have a new layer of abstraction. So what we'll see is this will be one way of creating code that is more adaptive to more situations. So we're going to work on a couple examples using some mathematical expressions today, but we can apply this to just about any type of program that you might want to write. Higher order functions give us a tool for building new kinds of abstractions. The other related reason is that higher order functions allow us to sort of encapsulate or package some logic and data into their own segments that are sort of hidden from other parts of the program. And so as we continue to work with higher order functions, this will be where environment diagrams really come into play as a way of illustrating that. And so these are tools that will be really useful when we learn new concepts like lists and for loops. There'll be another use for higher order functions there. But I will warn you that higher order functions themselves are one of the trickier concepts in this course. So if this feels foreign and weird at first, that's okay. But go through the examples that we're going to work with step by step, play with them in your own interpreter, make use of Python Tutor as a step-by-step breakdown of what's happening. And the more you practice, the more they will start to make sense. So with that, what is a higher order function? A higher order function is one of two things. It could technically be both of these, but a function that takes in another function as an argument. So we're used to right now having functions that take in words, numbers, maybe a Boolean as an argument. That is quite common. It's something that you will be doing a lot. But another kind of argument is a function itself. And so functions that take in another function and call that function are a higher order function. And similarly, a function that returns a new function as a result of some computation is itself a kind of higher order function. And so these are the two types of things that we'll be looking at today. In later segments, we will revisit both of these with more complicated examples as well. So one of our first examples is going to be looking at some math. And one of the things that's pretty cool about higher order functions is how they allow us to generate a single function that is very adaptive. And so in this example, what we're going to start off is we're going to look at how we can sum numbers. So you may have seen in math class that we can express things as a sum, in this case from 1 to 5. And what we're doing here is we're just adding, in this case, k, the terms of k, 1 through 5. And if we sum that up, we get 15. But we can express sums in all different kinds of ways. There are things where if we needed to sum cubes, we can sum from 1 to 5 with our term. That's a word that we'll use later, but it doesn't really matter, is k to the power of 3. And so in this case, we are summing powers of 3. But there is also this pretty neat expression that allows us to approximate pi. So pi is an irrational number, right, that has an infinite amount of decimals. So most often we need to approximate it. So one of the approximations of pi, and trust me, you don't need to have this memorized. You don't need to know why this formula exists, but it will be useful in illustrating a use for higher order functions, is this function 8 over 4k minus 3 quantity times quantity of 4k minus 1. So this is one of our expressions that lets us approximate pi. And so what we're going to do is use higher order functions to build our own generic summation function. and that will be one of the examples that we work with today. So let's hop on over to Python. And right now I'm in a just empty interpreter. And we're going to work our way up to this example. So the first thing that I want to point out is that we have print as a function, right? I can say print hello, and it prints something hello back. When we're working with functions as data, there's something that we've been doing all the time so far in this class, which is we've been calling these functions, but we don't have to call a function. We can just type the function without parentheses, and what that gives us is an expression, which is just a representation of this function in Python. So you will notice we just type print. Python tells us built-in function print. And what that means is that we have a function over here called print, but we are not calling it. We're just referencing that data. So I can also do things, something like this. Let's call it my print is equal to print. And what I've done is I've given a new name or a second name for the print function. I can still, of course, call print in the way I haven't modified the built-in function, but I can also call my print. And so what I've done here is just give a function a new name, and if I actually evaluate that function, Python happens to know this is still the built-in print function because that is what my name is set to. But this is really useful to know and to think about, which is when we want to use a function as an argument or to return something, what we're essentially going to think of this as doing is just leaving off the parentheses. We're going to treat it as a value by choosing not to call the function. And so in our next examples, that's what we're going to do for some of these. So let me pull up some examples. And the first couple, we're going to just work with a few things. So I'm just going to paste these in so we don't have to type them out. We're going to have a couple functions that look at the area of something like a square or a circle. So pi, if we import it from the math module, so this is something that we don't really talk about too much, but you can import a bunch of tools that Python has that are broken down into modules. So the math module has a value for pi, and we can use it in our programs. So one thing that's great is we can do things like, let's say, the area of a square with a side length of r, or in this case, we're going to put in 2 for the value of r. 2 times 2 square has an area of 4 inches, feet, whatever it is. This is not a physics class, so we're not going to care about the units. But, so be it. We can, of course, any value that we put in here, what Python's just going to do is square that value. We have a circle, and we can put in the area of our circle, and this is pi r squared. So we've got 16 times pi, 50.2 sounds about right. And so you'll notice something here which is kind of interesting between these two functions is in both these cases we have r squared times, in this case, pi. And so there are some other functions that we might potentially want, or shapes that we might want to know the area of. And so I'm just going to move this up here. One of those could be a hexagon. And so the area of a hexagon is r squared times 3 times the square root of 3 over 2. Again, this is a formula that you don't need to know at all, but it exists as a formula. And essentially this just captures the fact that hexagons have a different shape. So if we were to ask for the area of a hexagon with a radius of length 4, we would get 41.5 as our area. And here again, we have another function that has r squared times some additional stuff. And so what we might notice is that we could abstract a lot of this logic away. Perhaps we want to calculate the area of any shape whose area is based on some standard, some standard format. So one thing that that we can do is just define a generic area function. And so this is going to take an R and what we're going to call a shape constant. And so we can say area and R can be 2 and our shape constant can be 1. And this would give us essentially the area of a square. And we're going to do this just for squares and circles. But we can define a couple functions that encapsulate this logic just by passing variables around. And so this is one of our first techniques of applying a rule that programmers often call dry or don't repeat yourself. And what this really does is it lets us reuse some logic across multiple functions. So what we've defined is that the area is roughly based on this r squared idea, and that we have some constant that we can multiply things. So if I wanted to, I can do the area of a circle with radius 4, and I'm back where I was before. So the math all works out. And so what do we do here? We abstracted some data. And all we had to do in this case is pass in a single argument into our primary area function. But sometimes we have something that is more complicated than that. If we're working on our summation, what we might notice is that this k is, if it's 1 through 5, it's just an increasing a number here. But in reality, k is a function of something, right? It is k times k times k in this case, or it is our expression 8 over this 4k minus 3, 4k minus 1 function. And so sometimes what we're going to need to do with k is to use a function where that value changes each time. So we can't just pass in an argument that already has a defined value. We're going to need to pass in something that we can later call and then get the value from. And so that's what we're going to do with our summation. So I'm going to clear the screen again, and we're going to work on a standard sum number function. And I'm just going to paste this in, and we're going to talk about and play with it for a second. So we want to sum the numbers 1 through 5. And so we're going to define this function sum number, and we're going to take in 5 and sum numbers. And we sum numbers from 1 to 5. And as was shown on the slide, this is just 1 plus 2 plus 3 plus 4 plus 5. We add that up, we get 15. So how does this work? Well, we start off with total. We use the value k to keep track of our position. And we can increase k until we get to n, or the number of numbers that we need to sum. This syntax here may be new to you. This just assigns 2 variables at once. So first it says total is equal to 0 and k is equal to 1 in a compact way. This is total plus equals k is total plus k, and k plus equals 1 is k equals k plus 1. So a couple different ways you can write some of this logic out within our loop. But this is one way of summing our numbers here. Now our second example, we used some cubes. Whoops. So if I wanted to do 1 cubed plus 2 cubed. Star in Python is the power operator, something that you'll learn. We'll just build up our knowledge of operators over time. There's a few different ways of doing this, but we could just start to add, we have a way of adding cubes. But one thing that we can also do is, earlier I imported the power function, and power just takes in a value, and the exponent, let's do 4, that we're going to raise something to. So 2 to the power 4 is 16 in this case. And so if we were to redefine our sum function, we could have a sum. I have the indentation off on this function. So let's see really quick if I can fix that. Nope, you don't like that. Oh, I see what's going on. We're missing a comma here. 1 second. So we can define a cube function, and sum cubes works the same way, where it will sum the cubes from 1 to n, and before, let's see if we scroll back up, before we summed our cubes from 1 to 3, just sort of manually, so we can verify we get the same thing, and we do. And so this is one way of writing our sum function. We have a while loop. We go from 0 to n. We keep adding some data there. But you'll notice that in our main loop, we've done the same thing. We have total, and we're incrementing our total. And what's changing here is the fact that we are, instead of incrementing it just by k, we now have a function of k to the power of 3. We're still incrementing k by 1, and this way is just a slightly more compact way of writing our same function. So one thing we can do is we can define a generic summation function. And this summation function is going to do a couple things. Instead of taking in just n, it's going to take in our term for how we increment our function. And then what we're going to do is we're going to sum using that term. Now you'll notice here that a term is just passed in as a normal argument, and when we want to use it, we call it with parentheses. So what should our term be? Well, in the case of just summing our straight numbers, we use a function which we can typically call identity, and this is just going to return k itself. So if we have summation, we can say summation of 1 to 5 with identity, and this gives us 15 back. So this is so far our same function, and really, if this was all we wanted to do, high order functions wouldn't necessarily be all that exciting. But what is cool is that we can keep building up our list of terms that we use. So in this case, we're going to define a cube term. This is k to the power of 3. We could also define a square term, right, which would be return k, and we could write this any way we want. We could have that be k squared. And so what we can do now is we can call summation of 1 to 5, and our term this time could be our cube term, and we get 225. So that's 1 through 5 cubed. And so what we've done here is build the first two examples on the slide. And so now what we want to do is use this approximation for pi. And we'll then play with what that gives us. So let's go back over to the interpreter and we'll walk through this. And so what do we need to make this work? Well, we're going to define a new function called PyTerm. So PyTerm itself is not going to be all that interesting. It just gives us back some decimal values. But it is 8 over a multiplied expression, k times 4 minus 3, and k times 4 minus 1. So the same setup that was in our on our slide. And so if we wanted to, we can approximate pi. So summation. So let's say we wanted to do 5 sums to approximate pi. We could do, we can call a summation with 5, and our term is going to be the pi term, and we get 3.04. So not a terrible approximation of pi, but maybe not so great. And so we could keep upping the value in the way that we approximate pi. So instead of 5, let's do something like 20. We'll get 3.11. Maybe we'll make this 200. And it keeps getting closer and closer to the value of pi. And so one of the interesting things that we can do, and this is a technique that you'll learn about a little bit in Data 8 and in other courses, is we can use computation to very easily approximate and measure the error in things. So the question that we might want to ask ourselves is, how much does this differ from the actual value of pi? And of course, I did not have this indented correctly. So let's see what happened there. Let me grab a better copy of this function. So one thing that we could do is just write a small function that prints the approximation of pi and what our error is. So assuming we just divide by whatever Python's built-in value of pi is. So in this case, we're kind of trusting Python as the ground truth, but for this example, that's good enough. It's a value of pi that gets used all the time, so we're going to assume that it works just fine. We can subtract 1 from our own summation and see how our approximation handles things. So we can play with this, and we could say, if I only use 2 terms to sum pi, well, I get a 7% error, so that's not so great. But if I do something like go back up to 200, my error rate now decreases substantially. And for a computer, this is pretty cool because it's very easy for a computer to run a loop over 200 values and to run a couple hundred multiplications and additions. That's really not a problem for a modern computer. But I can even do something like, if I did 20,000 summations, something that you could only do with a ton of time on paper, we can see we get an incredibly low error rate for pi. And I can even just for fun add many zeros. And at that point, it starts to take a little bit longer, but you'll see that this is e to the -6 spots of error. So as we keep increasing our summation, we keep getting increasingly more accurate results. And so this is one of the interesting things, that by using harder functions, we can build tools that really take advantage of building abstractions. In this case, just playing with pi and approximating pi is a particularly interesting example, but the point here is using something like PyTerm as an argument that is itself its own function. And so that's where we're going to leave this video today, is we can now use a function as an argument to another function. To call a function that has been passed in as an argument, we simply add parentheses to that name. And so this is our first example of using higher order functions in a somewhat interesting way.